It really is designed to be sort of plug and play, where you can provide thread scheduling, networking, almost everything you can think of that's platform or database specific to Accord, and still have it not know your data model, not really know anything about your topology except what's absolutely necessary, etc. And so Accord provides a range of interfaces to facilitate this. So ways for you to describe your transactions, ways to specify, well, here's how this transaction executes reads, here's how it executes writes, here's how it generates results. And then there are actually some extension points where you can modify the actual transaction execution logic that Accord uses. So you can say like, hey, I want to inject this custom implementation for the execute phase or the persist phase, and a bunch more. So getting into the anatomy of a transaction, it's actually, there's a transaction object or interface, and it's really just implemented by transaction.inMemory. And so the transaction object is something you really only see at the coordinator. I'm not sure, I don't recall offhand if we ever constructed them at recovery coordinators. Mostly inside Accord, you deal with commands, which are sort of a local representation of the components of the transaction you happen to know about at a given time. So transaction.inMemory has basically your reads, your writes, your updates, what keys you're going to touch, etc. And it's what you pass to Accord that says this is my transaction I want to run. Transactions have a domain, either keys or ranges. You can only pick one, and ranges currently are really only used for range reads and sync points. There's no notion of like a range write transaction. Range transactions are a little more expensive, so Accord does dependency tracking, and if you have a very large range, like the entire hash ring, then the potential metadata you might need to consult on a large system with many in-flight transactions could be large. So it's always something to keep in mind when you're trying to engineer things that use range transactions, is that in a given situation, the dependency management may be a problem. So you kind of want to keep those on the smaller end. Keys and ranges can span any tables managed by Accord. So Accord supports multi-key transactions, and actually in a range transaction, Accord would also be happy to do a range scan on multiple tables. It wouldn't actually care. Keys and ranges, Accord's not really aware of tables. It's not really aware of your data model. It just knows there's ranges and it can compare them. And so, for instance, you could have like a collection of ranges, and it could actually be multiple tables, or a collection of keys, and some of those keys can be from different tables. And we're going to get into that pretty soon. And so, like I said, Accord itself is table oblivious. So like when Cassandra represents or presents the topology to Accord, it just says like, hey, I have these ranges, I need you to distribute them so that I can then do read and write operations on them. So Accord just knows that it has a splitter, and it knows like I can take this range and I can split it into small components. I can also get sort of a sense of how big they are so that it can balance them. That's it. Otherwise, it doesn't know that these ranges actually represent tables, potentially different tables. So there are a couple different kinds of transactions: read and then write, which is optionally read or write. And then there's ephemeral read, which we use for linearizable read transactions for a single key. It's a weaker consistency operation. So if you try to use it for multiple keys, you would not get linearizability or strict serializability. But we don't actually do that. We just use it for a single key where it keeps the guarantees we're trying to maintain. And then there are sync points. And so sync points are barrier transactions I've mentioned before that create a happens before relationship between that transaction and any acknowledged writes that occurred before that sync point. And so the sync points will let you know that the side effects of those transactions are visible at either quorum or all. Not super important for users. It's used heavily by migration. And it also could optionally be used. You can access these via repair. And if you're using an external tool that's going to look at like raw SS tables on the file system, you can get these happens before barriers using sync points, which you would access via repair. So let's get into keys. So I mentioned that keys are prefixed with table ID. so that you can have, that's because an Accord can't actually see that. There's no method on the key interface for Accord to go get that. It doesn't really care. It's just got keys, and they can conflict with each other if you are doing multiple overlapping transactions. Key is essentially analogous to Cassandra's decorated key class. So a decorated key has the partition key as a byte buffer, and it has the token, which is the hashed representation of that key. And it doesn't include clustering. Accord never has to deal with clustering because our data distribution model in Cassandra, we don't allow you to split a partition. Data is distributed at the granularity of a token. And so when we have exposed that in our implementation of keys to Accord and ranges, we've sort of maintained that and not tried to pick something more granular. And the benefit there is that when we have these keys in a memory, they don't have to include the clustering that we're not really leveraging anyway. So it just makes it a little more compact. There's also something called a routing key. And a routing key is essentially the same as a token or ring position. So ring position is the interface that token implements, and a token is the hashed representation of a partition key. And so that is a routing key, and we have Accord routing key, which implements the routing key interface. We'll go into a little more detail on that later. So then we have ranges. So in Accord, let's go with, first of all, ranges. The ranges themselves aren't prefixed with a table ID, but a range will have a begin bound and an end bound, which are, they can be, I think, keys or, no, I think with ranges we only use a routing key, not a key. So we only use essentially the equivalent of range ring position, which is also range token. And that's implemented by token range. And there aren't other bounds. So like in Cassandra, there's like abstract bounds, and then below that there is like bound and range, and bound itself can actually be configurable, whether it's start or end inclusive, I think. And those aren't used or needed in Accord. Those bounds become really important when you're trying to do data reads like in the middle of a partition. But we kind of get away with not using them in Accord. I'm going to explain why in just a second. So yeah, there's a couple subclasses of Accord routing key. And again, Accord routing key is what the bounds of ranges are in Accord. And these provide a couple different pieces of functionality. So we have token key, which is kind of what we're all used to, right? Like it's just a point, it's a ring position. And so there's different bounds on the ring, there are tokens. There's something that's unique in Accord, which is sentinel key, which provides minus infinity and positive infinity. So there are no wraparound ranges in Accord. So Cassandra doesn't have a positive infinity and negative infinity. So it has to have wraparound ranges, which is a lot to deal with. Accord instead has these bounds that you can just put at the end. That means like it doesn't wrap around, it just goes forever. And there's no real token that is less than minus infinity or greater than positive infinity. There is another wrinkle there where you have like token key and sentinel key. There is actually a prefix on those, which is, are these a minimum version of this, or it's a postfix. Are they the minimum or maximum version of this key? And what that means is, let's say you have a token key and it's the minimum version, then that minimum token key is less than the actual token key, but still greater than whatever that token key minus one would be in that partitioner. And so one of the things this allows us to do is we don't synthesize keys that are like one greater or one less. And there's a couple different scenarios where that's advantageous. So one of them is that Accord will frequently have a key and want to convert it to a range, just to access or do some comparisons against collections of ranges. And by being able to synthesize a range out of a key that's still valid, we can use min and max token keys to take any token or sentinel, convert it to a range. Additionally, the range in Cassandra, I believe, is begin exclusive, end inclusive. And that's fixed in Accord. You'll see some code that makes it look like Accord supports more than that, but in practice, right now we only use range as the corresponding inclusivity as in Cassandra. But then when you go to do range reads, you have the problem of, well, if you're not going to synthesize a token when you have like less than or equal to or greater than or equal to, how do you implement that? Because you're not synthesizing, token plus one to implement that to fix the inclusivity or exclusivity of range. But with min and max token keys and sentinel keys, you can implement something that actually behaves like less than or equal to or greater than or equal to. All right, maybe a little TMI. So next is seekable, unseekable, and rootable. So these are all interfaces that are could apply to multiple things that are like key-like or token-like. So seekable is the first one I'm going to talk about. All of these are always prefixed with table ID. There's like no use for a scalar value in Accord that isn't prefixed with table ID because you wouldn't know what it applies to. So a seekable can be either a key or a range. So a range is considered seekable, but the bounds in it are only going to be rootable. And I'll explain rootable in a second. And a key is going to be seekable, and it's going to have the token and the primary key, and it's actually going to have both. So you will always be able to get the primary key from a key or a seekable. Seekables, whenever you see the plural, well, that's just a collection, and it could be a collection of keys or a collection of ranges. So then we have unseekable, and so this is either a routing key or a range. And so yes, it's odd. Range is both seekable and unseekable. It just happens to be that there's no conflict of implementing both just from the way we use ranges. And so the goal of unseekable, just like the goal of token, is just to be more compact, right? You don't need to include the entire partition key. And then you have collections of unseekables. And so those are like routing keys or ranges. So when you're using Accord or looking at Accord, it'll be asking for these different collections. It's kind of helpful to know what they are. And so like seekable just means it includes the partition key. Unseekable means it is just the token. And rootable means that it could be either, which means like I implement an interface and I don't really care whether someone gives me an unseekable or a seekable. I could accept either. And one of the places where rootable is helpful is that seekable does not implement unseekable, even though you can trivially convert any seekable into an unseekable, just kind of by definition, right? The seekable already has the token, therefore you could strip out the primary key and get to an unseekable. All right, so one of the other key interfaces is data. And so from Accord's perspective, it has no idea what this is. So generally when we have an operation that Accord is executing on your behalf, and it's probably actually your code it's invoking, that code goes to give Accord this data, and it's something that has to be serializable. And the only thing Accord does with data is merge them together. So if you have a transaction that's like a multi-key transaction, different command stores are returning results for different keys, you actually need to be able to merge those together so that they can then be sent to other parts of your transaction plumbing to be then picked apart to execute your transaction. Because again, Accord doesn't really know your query language, your data model. It just kind of knows what you've told it about how to distribute and execute transactions. So we implement that with the transaction data, which is a glorified map from integer to transaction data value. Transaction data value can be either transaction data key value or transaction data range value. And transaction data range value is necessary because it's a little more tricky to do range reads because range reads might have limits and a lot of partitions might return some results, no results, and you really will need to merge them. Whereas transaction data key value, you don't really need to merge values because by Accord's contract, any replica you read from should always be 100% identical. So that actually, its merge behavior for multiple reads for the same key is just to stomp on them and replace it. But also, by design, Accord never actually should repeat the same read multiple times and put them in. We'll talk about how that integer is structured a little bit later. So then there's the result interface. So you can get, when you have to give the Accord coordinator some way to calculate the result. And so there's query, which I'm going to go into next, that actually does that computation. But result is the interface that's returned. It has basically no methods on it. It's just a marker interface. Could even be object. And we actually use transaction data to return results for key reads. We use transaction range read result for range reads. So that result, like I mentioned earlier, is a little more complicated because of having to do more interesting merging and repeated filtering and limit. And then there's retry new protocol result. So when a transaction is misrouted either to Accord or Paxos, we have this retry new protocol result, which we send to the coordinator to say, hey, you raced with some change to the schema, and so we need you to retry on the other transaction system, so that, because we can't accept it here. Read. So read is basically a description of all the reads you know at planning time that your transaction is going to do. And it all does have to be known at planning time. So that's like a core feature of Accord's interface, is that you declare upfront all the keys you're going to touch. You can't, do the reads and then find out, like, I want to do a second round of reads, or I want to read some, or write to some additional keys. You have to tell all of them upfront to Accord. That's what the keys interface on reads does. It just says, like, here's the list of seekables that, or it might be keys or ranges that we're going to touch. There is a slice and split method. So this shows up in some of these interfaces where Accord can say, hey, I need you to slice, produce me a reduced version of this read that only includes things that intersect these ranges. And what Accord will leverage that for is only persisting the portion of the read that applies to that range at the shards that store that range. And so it reduces the number of copies, right? Like if you have a 10 key, 10 shard transaction, you don't want to store all 10 reads at each shard. It's wasted metadata overhead. But then the inverse of that is merge. On transaction recovery, it might actually need to read back all those reads and merge them together and then try to execute them again. So that's implemented by transaction read, which returns data, and this data is completely opaque to Accord. So transaction read itself is really just a collection of seekables, and the name, that integer I referred to earlier in transaction data, is basically a counter that's basically incremented at planning time, and then a prefix, some number of bits prefix that is the type of the read. So there's actually could be a couple of different independent counters in the planner that's incrementing these IDs. And so there's user. So if you have a transaction statement with a let, those will get the user prefix. If it's the returning select, it'll get the returning prefix. If it's an automatically generated read for SQL operations that aren't reads, but may implicitly require one, like list append, I believe, or set. So those get encoded as auto reads, and then if it's a cast statement, the read for that gets encoded as a cast read. So transaction name read supports both ranges and keys. It's used for both types of transactions. It's invoked with the intersecting keys and ranges at each command store. So you'll get that slice, right? And then that slice will be sent to each node, and then that node will invoke the transaction read at each intersecting command store and explicitly provided a list of keys for just that command store. So the slice is per node, which is really per shard. But when it's invoked, it actually has to be explicitly passed the keys so that each command store knows the subset to execute. So and then these reads, if you have multiple reads, they all execute concurrently on the read stage. There is a read consistency level that is included in transaction read, but Accord's not aware of it, and I will get into later how that works. So then there's query. Query runs entirely on the coordinator, and it only has one method, compute, which takes in all the data from all the reads. So you're basically getting transaction data in Cassandra. And then everything that Accord has read for your transaction is in there, and you kind of have to make a decision as to what you're going to do with that. And it's going to return some kind of result object. As I mentioned earlier, there's 3 of them. So transaction query has a couple different subclasses for use by different kinds of transactions. So most of these include validation to check that that transaction is supposed to run on Accord rather than supposed to run on Paxos. And so it can generate the retry different system error before going any further. And I think all of these, maybe except unsafe empty, do that. So there's all, which just returns all reads, and that is used by transaction statement. What happens is that outside of the transaction statement, it'll get the transaction data and it will just pick out the one value it actually needs to return based on the ID. There's none, which returns nothing, and that's for non-serial writes, but it does do the validation. There is condition, which is used for checking a Cass condition and returning a result that is specific to the semantics of Cass for our Cass SQL syntax. There's range query, which does the final level of results, merging the results from multiple command stores and then reapplying the limit, because reading from multiple command stores concurrently can result in going over the limit. And then there is unsafe empty. And so this does no validation at all. It's used for Accord system transactions, basically like Accord for durability scheduling. You may schedule sync points, and for that, it doesn't want to have any query at all. It just needs something that can safely be serialized and sent in messages. Then there's update. So update runs entirely on the coordinator, and basically query and update, they're called sequentially. I've tried to keep it so that query is called first, then update, but it's not a strict contract. And it supports keys, slice, intersecting, and merge. So if you have unconditional updates, right, it could be potentially quite large, right? You could have like a 5 megabyte update and a 1K update, and you wouldn't want to persist that 5 megabyte update at multiple shards when it only applies to one of them. So that's one reason it's very valuable for update to support slice and merge. So when you call apply, it takes the data from the read and returns a write. So transaction update, which implements update, what it does is it completes the fragments of dependent writes, and then it also just returns back the non-dependent writes. So the ones that are just kind of blind writes, not conditional on anything, it just returns them. And then if there's writes that are conditional, it completes them. Transaction update, one very important thing it does is that it sets the timestamps for the values being written. That also can include for like lists, updating the cell path. So the cell paths are a whole thing. I'm not going to get into it, but how those are generated is very important for getting the semantics correct. It is not necessarily the transaction ID or the execute at hybrid logical clock generated by Accord. There's like an additional layer there that goes in to make sure these values are unique and monotonic. And it is based on the execute at, but there can be collisions, so those have to get resolved. There are instances where our integration, we choose to preserve timestamps and not use this timestamp generated by Accord. So like hints and batch log, those are like replay cases where we're taking something that was already committed to do in the past at a specific timestamp, and we are just making sure they propagate. We don't want data resurrection. Like if someone deleted that, we don't want to override their delete by giving it a new timestamp. And then there's using timestamp. There's no situation where you specify using timestamp and Accord will never use its own timestamp for anything in that transaction if there's any using timestamp present. There's also a write consistency level that is in transaction update. It's also not visible to Accord, just like the read one, and I will get into why that is. So write, it's implemented by transaction write. It does not happen to be splittable or mergeable. All writes are sent to all shards. I think this has to do with transaction recovery and just the complexity of making sure that if you need to recover a transaction on a shard, you're not missing, you may not be able to read the data you need to recompute the writes, but so then if you come across it, you have to have at least the side effects available. And shards are all sort of independently cleaning up and truncating committed transactions. Right now the approach is to not split the results of write or update. And these are invoked with intersecting keys, each command store on each node, and then they're passed to the mutation stage to be executed. And again, these have to go through the command store. Like the reads and the writes have to go through the command store at each node so that they are sequenced correctly relative to any dependencies. Like that's what command stores do. So putting it all together, and this is like a survey slide. Not supposed to remember any of this, but once you have all these components, you can then go look at all the places we construct different kinds of transactions, right? So there's transaction statement, there's cast requests, which can be converted to a Accord transaction. There's mutate with Accord async and consensus migration mutation helper. So like non-serial writes use this, batch log uses this, hints uses this. Storage proxy has a read with Accord method, which is basically how you read for both paging and non-paging use cases. Blocking and read repair has repair via Accord transaction. I'm going to discuss blocking and read repair later, but when we're trying to have all writes go through Accord, that actually includes blocking and read repair. And then for range reads, range command iterator has an execute on Accord option where it could find a range that intersects with just Accord and execute part of that range read on Accord. All right, deep breath. We've gotten this far, and now we have to run Accord and Paxos at the same time. And we've actually already talked about a lot of this, so I think this is the part that's going to have a lot of overlap with what I've already gone over. So as discussed in the previous session, Paxos consensus is on writes and the timestamp. So when you need to recover a Paxos transaction, you already know the writes. So you don't need to recompute on read or on recovery. So Accord's consensus is on transaction definition, dependency superset, and execution timestamp. To recover an Accord transaction, in a lot of the cases, you will need to recover data because it may have reached the stage where the transaction is committed, but no one has actually persisted, done the reads, computed the outcome, persisted even a subset of the writes for you to go and collect. So recovery in Accord, because it's going to recompute, needs reads to be deterministic. This is part of what command stores do, is they execute things in a deterministic order. But non-serial writes don't go through command stores. They don't execute in any predictable order. They can be hiding at a minority. So, and there's some other differences between Accord and Cassandra, right? Like what Accord wants to do is read at one, which means by default, it would not be able to see quorum writes done at any time. Accord also does asynchronous commit, which means that things that are trying to read Accord's writes aren't going to necessarily see it, even though the Accord write has been acknowledged. Additionally, Paxos and non-serial reads, are just unsafe to read Accord writes. So how do we bridge the gap? So the first thing is we have to stay highly available. So that means, at least in the request path, we can't do any operation at all. It has to be at quorum. But in the background, when we're migrating from Paxos to Accord, we can run repairs to replicate data at all. And that satisfies Accord, right? Accord wants to read from one replica. That's just how it works. So our goal is to repair things at all. But when we're migrating from Accord to Paxos, Paxos generally reads at quorum, at least in the use cases we support. So does the non-serial. So Accord just needs to replicate the data at quorum. So Paxos and Accord both reject misrouted operations. I'll go into a little bit more detail on that later on. And when there's a misrouting, one of the goals was that you shouldn't see a client error, right? The coordinator should transparently retry on whatever system is currently active, so you don't see elevated error rates. And then there's key migration, which I talked about in the previous session, which helps ensure visibility at quorum. And again, key migration has to be, since it's has to be highly available, right? Key migration is what we do before an individual transaction, when we know, like, I'm going to operate on one key, in Accord's case, n keys, and we want to make sure that any unresolved Paxos transactions are visible. So there's like a single key Paxos repair for Cassandra, and there's a single key sync point from Accord. And so those are kind of the primitives we're going to use to bridge this gap. And now we go into like, okay, well, how do we bridge it? So one of the other wrinkles is the not having non-serial key migration. So like we need this always online primitive that we can do a quorum that can find anything that may only be visible at a minority and persist it at least a majority. And we can't do that for non-serial writes. There's no metadata. There's no first round of Paxos that you can go consult some system tables and find it. So for Accord, we had to migration to Accord. We had to split the migration into two phases. So in the first phase, we write through Accord, and we still continue to do CAS with Paxos because CAS has to read at quorum, and that means we need to use a consensus protocol that can tolerate the reads not being deterministically reproducible. So in phase one, Accord writes at quorum with synchronous commit, and then we're going to have a second phase after a data repair completes in phase two. At that point, Accord can safely read all of the non-serially written data. It can't safely read the Paxos data written by Paxos because Paxos overlapped with the repair we just ran, and that's why we need two repairs. So in the second phase, we can run Accord transactions, but after key migration in Paxos. So Paxos, may have been committing at any, and so we do a key migration. We make sure that the last Paxos operation was migrated at quorum, and then Accord can read it. And so in the second phase, we've stopped using Paxos entirely. Then after a Paxos and data repair, Accord can run normally. So that means it's doing asynchronous commit and it's reading from a single replica. Okay, so how does Accord read a quorum and write a quorum when Accord proper, at least core, doesn't understand that? So that's something that we actually do sort of with customization in the Cassandra codebase by basically injecting custom components. So Accord has a coordination adapter. I think you provide the coordination adapter as configuration at startup for Accord. It's not like and there's you provide a factory, and the factory chooses which one you get. It can actually inspect the transaction and decide which one you get. And then there's these extensions of Accord's implementation of some things. So, for example, Accord has execute, I think, for the execute phase. The execute phase in Accord is after you've done pre-accept and accept, and now you're going to actually start doing your reads. And so that supports reading at a configurable consistency level. It also supports reading with read repair. So that means that if Accord is reading data that is not persisted at all, it's possible that it could find replicas that are inconsistent. As things are structured currently, this should never happen. It's not a supported use case. There's, again, there's code to do the read repair, but you've already lost determinism by the time you're doing that. And so there's a metric for this. It should always be 0. And then it also helps with applying read repair mutations from non-Accord reads. So there's some optimizations there to make that more efficient. And so we actually do that in interop execution. We'll cover that later. There's Accord interop persist, and that supports synchronous commit. And basically what it does is it just injects some slightly different response tracking and request logic. And it's the same thing with read. So in Accord, like persist, the messages for that default to sending a response before anything has actually been done. And so there's a slightly different version that actually really waits for the persistence to have taken place. And then also to wait on, whatever your consistency level is. And there's a similar thing with read, although the async versus synchronous issue doesn't exist. So Accord interop execution, kind of how does that work for the various things I just told you it does? So there's a new read coordinator interface. You'll see that in the Cassandra codebase in a couple places. And so there's only 2 types of read coordinator. There's the Cassandra one, which is for an eventually consistent operation. You'll have one of those, or you might have Accord interop execution. And what that means is that your read is running inside an Accord transaction. And so that Cassandra plumbing that used to just do eventually consistent things is actually like, if it sends a read command, it will actually go through a command store and only run when all dependencies have been satisfied. And so that's how you're getting linearizability. But you're still going through, for instance, abstract read executor, which had a lot of code that we didn't want to end up rewriting. And so to give you an example of some things we get out of reuse, right? Like Cassandra has specific logic around selecting replicas, dealing with short reads, and performing blocking and read repair. And a lot of those don't really exist in the same way in Accord or at all. So blocking and read repair, complex situation. So there are kind of three cases now where you can enter into blocking and read repair code. So you can enter from Accord. I mentioned that Accord, if you're reading at quorum, will do read repair. And so you might enter from there. And the read repair will generate some mutations to send, and they'll get sent immediately in the same transaction. So there's non-Accord read repair. And so you can go into a blocking read repair, find out that the read repair actually needs to be applied via Accord, create a transaction to go do that, and then that will eventually filter back to the control flow for the original read outside the transaction once the mutations have been applied. There's a bit of fanciness here. One of the optimizations in read repair is that it sends a unique mutation to each replica that is just what that replica is missing. There's real-world use cases where that selectivity is really important because you can accidentally exceed the message limit size without that sort of intentionality. So read coordinator has a send repair mutations method, and that will do slightly different things depending on whether it's the Accord one or the non-Accord one. Non-Accord ones, as I mentioned, creating a transaction. Something that's kind of unusual, if you ever take a look at it, is that the read repair mutation that is sent as an Accord transaction is sent as an unrecoverable repair update, which means that if the original coordinator attempting to effect this read repair goes down, those read repair writes will never, it'll never attempt to actually repeat them. Kind of the basics of that is that the read repair mutations you're submitting, you're reproposing old values. So if that data was written by Accord, well, either your transaction will apply it, or it will have already been applied by a previous transaction. If it was data that was not written by Accord, well, you're already kind of in trouble. Because as I mentioned before, like Accord doesn't want to read data that hasn't been written at all. But net of it all is there's no real reason to make it recoverable. And by doing it this way, we can basically eliminate a round trip having to wait on, because you don't have to wait for apply to go do this. All right. So routing. I think I've already talked about this quite a bit, but the different operations can end up split across Accord and non-Accord. Accord's ownership of things that it's going to modify are based on token range and table. And so you have like a batch that touches multiple tables or just multiple partitions within the same table. And so what we do is we split them. And this can race with configuration changes. And so we have to deal with those races. So in Paxos, the way we deal with that race, and also is to, if you get past the prepare phase, then your transaction is going to take place on Paxos unless you get interrupted and invalidated, right? And so that, you have that one shot to, complete when you're racing to collect a majority, and then that determines the outcome. And then Accord will come do a Paxos repair on that key, and it will make permanent one outcome. Either it did occur on Paxos or invalidated if it didn't occur on Paxos. And so that's kind of the interaction between, racing proposers from one trying to run on Accord and one trying to run on Paxos. Accord, when it determines an execute at for a transaction, the execute at actually includes an epoch that is one-to-one correspondence with an epoch for cluster metadata from transactional cluster metadata. And that includes what ranges are migrating and what phase of the migration they're in, which means that once a transaction has an agreed on execution point, it has a deterministic outcome for either it runs on Accord or it does not run on Accord. So that's how Accord does it. It doesn't mess around with majorities or anything. It just says this occurs in this epoch, and in this epoch, this was the migration state, and this is the outcome. And then non-serial actually works similar to Paxos. If you collect a majority, then your thing is acknowledged and it occurred on non-serial. If you don't collect a majority, well, it's persisted a minority. We are already tolerating that, and it'll be retried on Accord. Then it'll either happen or won't happen. So repair is what we use to provide, again, a happens before edge for a lot of these things, for all the keys, in bulk. So key barriers. Already talked about this quite a bit. So Paxos does the key barrier before prepare at each node. And that's actually, it's kind of hybrid of being done both locally and remotely to try and make it so that it's locally you just check and it's probably already been done. So the coordinator in Accord, what happens is, Paxos key barriers is we create a transaction for replicas to listen on if needed, to know that the barrier has been completed, and then just wait for it. And if it's already been done and Accord knows this from metadata, it just says barrier's done. Great. So Accord, in a lot of ways, is self-caching in that respect. So the Accord coordinator, does Paxos repair before an Accord transaction, and that's already in the code base. It's part of Paxos v2, and that just persists the data at quorum for that key from the Paxos metadata. Let's see. For non-serial operations, you'll also get key barriers. So this is part of providing linearizability from Accord, right? Even for non-serial operations, once we say it's running on Accord, we want it to be linearizable, so you do get a key barrier. So the coordinator does not do range barriers for range reads. I did talk about that a little earlier, and the reason is that it seems kind of unlikely that we would be able to complete range reads in time for a lot of query shapes if we had to run just that large number of barriers to make sure that was going to work. And these are the same documentation links as the last presentation. Anyone know what time we end?
4 minutes ago.
4 minutes ago. Okay. Yeah. Well, that's why I flew for a while. Okay. Any questions? Too much.
It's a lot.
Yeah.
Thanks for this walkthrough. I don't feel like I understand it in full, but I feel like I have a better understanding of what I don't know, and good handles on docs to go dig through the classes that participate in transaction management.
This is largely a translation of SQL on Accord at docs. So the part of this is you can re-reference the slides or reference those docs.
I didn't see it in here, but is there going to be support for guardrails?
There's
for instance, adding a guardrail.
Yeah.
Or example, how many select queries you can put in a core transaction? Because that's kind of what.
Yeah.
That's already one.
Guardrails is a complicated topic because we kind of need to investigate the safety of guardrails as a feature when interacting with Accord. So Accord requires deterministic transaction execution, and divergent guardrail configuration across nodes could be a source of non-determinism. That's something that needs to be rationalized in a sort of a fixed way where things that could cause non-determinism in Accord are clearly marked as such, and their configuration kind of needs to be managed in some way that interacts well with Accord. So rather than flat configuration files that can diverge per node, it really needs to be in transactional cluster metadata so that Accord knows for this transaction, the guardrail worked like this.
It is also a huge problem for transactional cluster metadata because it is also deterministic on every node. And if one of the nodes think that the result of execution depends on a certain thing that is in the file and it fails or proceeds in some other way, then yeah. But we did have a conversation with Stefan on mailing, maybe not the mailing list, but we wanted to do a CEP about that, about guardrails in TCF, but unfortunately, I don't know who exactly dropped the ball, but the ball was dropped. But it is very important for both, or anything that is deterministically replayable.
So the answer is like right now, I would literally need to go guardrail by guardrail and figure out which ones are safe and which ones aren't. That is not something we have done yet. And ideally, we can get them all in into transactional cluster metadata, but also I think add tests because we need to make sure the error handling really behaves the way we expect. Because Accord, I think right now, Alex, like Accord doesn't really understand the notion of rollback, right? Like if it says you should commit this transaction and do these writes, it, as long as the outcome is the same, you'll kind of get a behavior, but I think we want to make sure the error messages propagate back in a reasonable way. Yeah. Is that good, Pat? Yeah.
I want to understand how Accord would integrate with backups.
Yeah.
Transaction boundaries. How is it?
So I think one of the features where you need Alex, join me on this. Alex? Our backup strategy, right? I think we need transactional snapshots. Like we need transactional table import, we need transactional snapshots, right? For backup so it doesn't Accord doesn't require it, actually.
We discussed it with Johnny yesterday, and the main problem is that what is a snapshot for you exactly in this case? Because you know that certain transactions were applied, but this is just some subset of transactions that got applied by the certain point in time. In order to ensure durability, you need to sort of like do a flush, do RX or durability scheduling, and then you can say something conclusively, but then how to coordinate it between the nodes. So there is no mechanism that ensures consistent snapshots across the nodes. It's not impossible, it's just it did not happen until now.
Yeah.
But simply grabbing SSAble's snapshot is probably worse right now than it was with the eventually consistent reads, because as Ariel mentioned in both presentations, commits and Accord are asynchronous, which means that by the time that the coordinator has responded to the client, you know that the transactions are in the journals of the corresponding replicas, but they are not necessarily even in some cases the applied rights are in mem tables, but in some cases they're not. So there is no guarantee of that. And the reads may have not even executed. So
I think we have to figure out how we want to get to where we want to get to. There's also combining SS table snapshots and journals and metadata into one backup.
Yeah.
Might get us to a better place. Because you could probably drop something in the journal that just says like this is a snapshot over some range.
Yeah.
Let's talk more about backup as well. The next talk is scheduled to start right now, though.
Okay.